Get the recording started, which I think is going now. Yes, it seems to be. Great. And with that, I can pass over to Christian to tell us about Kokkos.
Yeah, thank you. Thank you for the invite to talk here and the opportunity to, present a little bit about what we've been doing. Let me get this into, right, there's the slideshow here. Okay, does that look good to you guys?
Yep, that looks great. Nice and full screen.
Okay, cool. So yeah, so I'm going to talk a bit about Kokkos here. What I'm doing is I'm going to give you a bit of an overview, a bit of a feel for, what we are doing, how this looks and feels. Obviously, this is going to be just a, small sliver of, what we've been up to. I'll give you some pointers where to find more information. Generally, I've been at Sandia for now almost 10 years. Have been working most of the time actually on Kokkos. I'm leading that project now. As I'm going to tell you later, the project itself is, quite a bit bigger than Sandia at this point. Most of the development actually doesn't happen at Sandia anymore, but at other DOE national labs. And we actually had a bit contact with your community already, largely via Fermilab and Brookhaven Lab here in the US. Okay, so why have we been doing this, right? So if you heard about Kokkos, right, Kokkos is, what I said, is for heterogeneous programming, right? In particular, it's the, the question of how do we write our codes without rewriting them all the time for different architectures. And what motivated us, right, was this, just that it's so extremely costly to rewriting our codes. Whereas this industry estimate, for like professional programmers, right, people at like Google and Microsoft and whatnot, that they can write about 10 lines of code per hour, which are actually usable. So that gives you about 20,000 lines of code per year, right? And if you make an optimistic estimate, right, you need to touch about 10% of an application to, say, switch from OpenMP to, I don't know, Circle or something like that, or from, HIP to, I don't know what. And if you look at our typical apps, as the typical apps we've had, in with our HPC community here, we typically write codes on the order of like 300,000 to 600,000 lines. So that's the applications themselves, right? If you then have to port like 10% of that, that means you have one person who doesn't do anything else than writing code, right? He doesn't do like, or the person doesn't do anything other than writing code, right? No grant proposals, no paper writing, whatnot. It takes about 2.5 years, right, to rewrite that thing. And if you look at some of these larger scientific libraries, things like E3SM, which is one of the US here Earth simulator thingies, for climate change or climate simulation, that's about 1 million lines. Trillinos is a big like HPC library, largely focused around like linear algebra and partitioning and stuff like that, which is about 4 million lines. These estimates kind of explode quite a bit. And so the idea is that instead of rewriting our apps all the time, we write our apps to and our libraries and whatnot to Kokkos, and then Kokkos is responsible for mapping to the vendor programming models and the vendor architectures. And that's what we've been doing over the last 10 years, right? And we have lots of different things, who are using Kokkos at this point, and that's spanning, the entire kind of HPC computational landscape, from computational fluid dynamics over molecular dynamics, electromagnetics, climate applications. There's all kinds of other stuff going on at this point. There's graph applications and some people here doing data analytics and stuff like that. So what is Kokkos? So Kokkos is multiple things. First and foremost, it's the C++ programming model for performance portability. And what that means is it's implemented as a template library on top of things like CUDA, OpenMP, HIP, etc. And one of our big goals here was that Kokkos is a descriptive programming model, not a prescriptive programming model. What that means is in Kokkos, you largely express what you want to do, but you don't get to control the details about how things are getting mapped to specific hardware. As a consequence, you are essentially forced to write portable code because we don't give you the tools or means, legally at least, within the Kokkos semantics, to write code which is too specific for or too much targeted to just a specific set of architectures. And another thing we are doing is we are trying to align with developments in the C++ standard. In fact, if the Kokkos team were an organization, we would be like the third largest organization in the C++ committee at this point. On top of that, Kokkos also is a bit more at this point. In particular, we've started to develop a lot of things around stuff you also need other than just a programming model. Things like math libraries, tools, profiling tools, debugging tools, auto-tuning tools, etc. And then, the whole thing is open source. It's maintained and developed on GitHub. It's licensed under a permissive license, BSD license, the whole thing. And, that's where all our development happens. And, at this point, we have quite a bit of users. I'm going to talk about it later. So I just said that Kokkos is this expanding solution of stuff, right? And that's where this Kokkos ecosystem comes in. Originally, we started with what is now called Kokkos Core, right? And that's the programming model. That's like parallel execution and like the core, like parallel data structures you need. When we have Kokkos kernels, which is like linear algebra kernels, graph kernels, and stuff like that, think MKL, QSparse, QBLAS kind of, capabilities. When there is like Kokkos tools, which is these debugging and profiling and tuning tools, which get you insight into not just our, the core programming model, but they also then allow you to, through that, to get insight into your applications themselves. We actually have explicit funding for Kokkos Support at this point via the Exascale Computing project in the US. And so that's responsible for doing things like documentation, tutorials, application support, etc. There's a number of additional efforts which are, kind of in the experimental state, I would say. One of them is Kokkos remote spaces. I'm not going to talk about that today here, but what that does is it essentially gives you the equivalent of global arrays and Fortran for C++, which are usable from within device code. So you can actually have global arrays which are usable from within, say, GPUs. There's Kokkos interoperability, where things which help you to interoperate with parts of your code which might be written in Fortran or Python. There's actually a new project which is coming in right now and which looks very promising, which allows you to write effectively Kokkos code directly in Python. What it does is it has a specific syntax for writing kernels, so directly in Python, which then get translated to C++ Kokkos and compiled via the underlying C++ programming models of the vendors. And that looks really promising. And then there's a project for resilience, which essentially looks at, how can we provide, some kind of capabilities for resilient execution. The whole thing has been transitioning to a community project. So originally it started, roughly in 2011, the project was started at Sandia. But at this point, we have a coalition of national labs here in the US who are developing this thing, led by us here at Sandia National Laboratory, but actually more code or more commits and more contributions are coming from outside of Sandia right now. So we are less than 50% of the total workforce now, I would say. A good part of that is coming from Oak Ridge in particular, and then also from Argonne and Los Alamos and Berkeley National Lab. one thing in particular the other labs are focusing on is the backends for their specific machines. So Oak Ridge has been, for example, the primary developer for the AMD support, considering that we are getting this exascale machine using AMD GPUs, while Argonne has been spearheading the development for Intel GPUs, considering that they get an exascale machine with Intel GPUs. Most of the other sub-projects, things like Kokkos kernels and resilience, etc., are largely done by Sandia right now. The Fortran thing is mostly Los Alamos, or led by Los Alamos, while the Python stuff is actually universities and Berkeley National Lab, which are largely developing. There's 3 papers, which are kind of the canonical papers now for Kokkos. 2 of them were just now published. And I think we don't even have page numbers yet, but they officially are out there. One of them, the Kokkos Ecosystem, is more like an overview paper for the whole ecosystem. So it's at a very high level, while then the other 2 here describe the programming model. Even the 2014 one is largely still, relevant as is, since we've been, pretty careful about backwards compatibility. And then Kokkos 3, the newer one of our programming model, is essentially describing development since that first paper. At this point, we don't really know anymore how many things are using Kokkos. We have only anecdotal, evidence for who's all using it. One thing is our main communication kind of vehicle and support vehicle is our Slack channel. So we have a Kokkos Slack channel. We have currently something like 660 registered users in there from somewhere around 90 institutions. I'm not sure if anybody there is actually working in Antarctica, might be, but they are at university and still over there. But otherwise, we have people from every continent, using Kokkos and asking us questions there. That Slack channel is really there for everybody, like you can ask super beginner questions, you can ask super detailed questions. We answer all of that pretty fast, often within minutes, since the whole team is basically on that Slack channel. Another thing where we can find a bit of evidence is from this exascale computing project in the US. If you haven't heard about it, it's a pretty big project, I'm not 100% sure what the actual budget is, but I think it's on the order of like $500 million for software development per year we're investing there. And ECP has this dependency list. So essentially, who depends on who, right? And in particular, what kind of software technologies are used by whom. And if you look at that, when you see there that within that ECP project, right, Kokkos is roughly in the same ballpark as things like BLAS and HDF5 and Fortran in terms of number of dependencies, and about not quite half of all the C++ codes and projects in where use Kokkos. So how does that work, right? So the primary thing in Kokkos is that we have these abstractions. And we have 2 sets of abstractions. We have parallel execution abstractions and data and abstractions for data structures. On the parallel execution side, that is reasonably common. So we have execution spaces, which essentially abstract where you execute and what the resources underneath it. We have execution patterns, things like parallel for, parallel reduce, parallel scan, task graphs, etc. And then we have execution policies, things like range policies and team policies and task policies, etc. So what you do is you essentially write your code in these patterns, right? So all your parallel code is expressed in these patterns, like the parallel for, parallel reduce, parallel scan, etc. And you tell then these things via the execution policies where to execute them, and also kind of, what kind of iteration space to go through and other kind of properties, for example, iteration order and stuff you can potentially control via execution policies. On the data structure side, we have kind of similar equivalent things. We have memory spaces, which essentially, where does stuff get stored. We have memory layouts, the basic data structure in Kokkos is the Kokkos view, a multidimensional array. Think of it kind of like a Fortran array, right? Just that you can actually change how memory is laid out or how things are laid out in memory, which means you can essentially control the mapping of indices to the underlying 1D storage. And what it allows us to do is it allows us to change access patterns via just changing types of things, right? You don't have to rewrite your code. You just change a type def somewhere, and the access pattern throughout your code, right, is changed, which is actually a necessity for different architectures, because in different architectures you need to access memory slightly differently. And then we have memory traits, which is also part of like type information on these kind of data structures we have, which kind of let you modify how data is accessed. For example, you can tell it, that, oh, this thing is going to be restrict, right? So I'm not going to alias it. You can rely on that. Or I want atomic accesses for every access here and stuff like that. And what we found is that if you have all these abstractions and you use them correctly and judiciously, it turns out that you are able to write, to express all the things you need in order to write performance portable code. It's expressive enough to give us enough information about intent and what you're doing to allow for viable and useful mappings to underlying hardware capabilities. So here are a couple of just a short overview of a couple of core kind of concepts or core capabilities in the programming model, right? So you have this parallel for, in the easiest case, you just tell it, oh, I want n iterations, and then you give it a lambda with the loop body, right? So the lambda gets the iteration index, and then the loop body gets executed. There's parallel reduces, this range policy here is essentially equivalent to, where you say, I just want to go from 0 to n or from 5 to n or whatever. The first one was always, implicitly a range policy going from 0 to n in the default execution space, while, if you explicitly give a range policy, you can explicitly give an execution space. Then reductions, we have all these, all the typical things you expect, right? So you can do different types of reductions, sum, min, max, min, max, min, log, and whatnot, everything from MPI, etc. There's tightly nested loops that allows you to loop over like multidimensional index ranges. You just get a multi-index there. This one actually supports tiling. So the T1, T2, T3 essentially here in that thing tell the thing, how to tile your loop, which is pretty useful for like caching purposes in like stencil codes. You can combine, that MD range policy also with a parallel reduce, right? So the patterns and execution policies are kind of orthogonal, right? So every pattern implements all these execution policies. Then there's non-tightly nested loops. You start with a team policy, and I'm just giving random examples here, right? This schedule dynamic would tell it, oh, I might want to do like work stealing here. I expect load imbalance. If you can do anything about it, do something about it. But you could also just leave that off, right? But team policy, what that does is essentially for nested things, right? So instead of getting an index, you get like a team handle for your nested loop, and that allows you to then start extra nested loops. It's very similar to the OpenMP team concept. If you had talks about OpenMP already, which I kind of assume. There's tasking, the data allocation, as I said, is this view concept, right? Where you give it like layout and memory space. All of these parameters are defaulted, right? So you could even just say view double star star and would just use the default layout and the default memory space and give you something. Data transfers happen explicitly in Kokkos, so you explicitly copy, data back and forth between different things. There's atomics, there's tons of different, execution spaces. I think I'm even missing the circle one on this one. The HIP one is expected to go out of experimental probably in the next 6 months or so. we are still fighting with compilers, so we're still working with AMD to get all the compiler things, but I'm going to give a bit of an update on that in a bit. There's all kinds of other stuff we do. I can't really go into everything. Suffice it to say that almost every capability, for example, in CUDA, is either indirectly used by us or explicitly exposed by us. So, you can do things like streams. You can create your own execution-space instances to have, independent kernels running at the same time, right? We expose all the different memory spaces, right? You can have UVM allocations, you can have host pin allocations, you can have whatever, right? We expose asynchronous deep copies, right? We expose the graph concept. I'm going to talk about that in a bit. We're exposing things like, effectively, we're exposing things like texture memory, etc. Underneath our team policy exposes things like shared memory, etc. Right? All of these things are there, But what I'm going to do is to give you a bit better a feel for how this looks and works. I'm going to go through a small example here, a conjugate gradient solver, which just introduces the kind of core concept in a step-by-step way. So what this is it's just a simple iterative linear algebra solver for sparse matrices. And there's really only 3 math operations in there, right? There's a vector addition, a dot product, and a sparse matrix vector multiply. So what we do here is we, for data management, you use the views, right? So for example, here with 2 examples, we have a view, we say here it's of doubles. The star is really not indicating pointers, it's indicating like runtime dimensions. So we have compile time and runtime dimensions, where each star indicates like 1 runtime dimension. So these are 1-dimensional views. In this case, I'm explicitly creating the first one in host space, because what I'm doing here is I'm actually wrapping some existing allocation, right? I'm telling it it's unmanaged, so I'm not managing this memory. I don't own it. I'm not going to deallocate it, or if this thing goes out of scope. But what I'm doing is I'm wrapping something. And then I'm creating another view here of the same size, and because I defaulted everything, if I compiled this for the GPU, then this thing will end up going, being allocated in GPU memory. And then I copy data over. So the first kernel is with XP, right? And it's the simplest loop, right? It's a simple data kernel loop. There's no dependency between iterations whatsoever. If you have a serial implementation, right, you start with an XP, you tell it, how many things, what the length is. You tell it the, pointer, maybe an alpha, a beta, and a couple other pointers, and then you have that loop, right? In Kokkos, you replace these pointers by Kokkos views. This n is technically not necessary because the views know how long they are, right? So you could actually get the n out of this. But just if you want, like just go over the first section of that, you might want to give that n. One thing here is we allow you to give all your kernels names, and these names are then used in like profiling tools, for example, and I'll show that in a bit later. We use the Kokkos lambda here. It's essentially just a C++ lambda with some annotations, like the host device and whatnot you need for maybe HIP and CUDA, but you don't need it for SYCL. So, this just hides that from you. And then you have the single iteration here, right? So that looks, fairly similar. So you have a parallel for loop, right? You have that label. The execution policy here is indirectly a range policy 0 to n. You just gave an n, and it, because it's in the default execution space, whatever the default is you compiled for. You get this iteration handle, the index there, and then the loop body, which is basically the loop body from before. Dot product, similar. The thing here is that you have a reduction, right? So in CUDA that might be a bit non-trivial unless you use Thrust. Because CUDA as a programming model doesn't actually have reductions. This is also like a bandwidth bound, kernel. And serial, right? You just get the 2 pointers and the n again, and you just sum up the elements. In Kokkos, what you do is you get, you create the place where you want to store the result, and you give this parallel reduce, right? It's now a different pattern because you do a reduction. Every iteration contributes to something. The lambda gets an iteration index and a thread local handle for the reduction. You sum up into that thread local, and then Kokkos will combine all these thread locals at the end and store them in this x.y. So the more interesting one is the sparse matrix vector multiply. And if you look at that one, right, you start, you loop over the rows, right? Then you have a dot product of a matrix row with a vector. And this is an example of a non-tightly nested loop, right? Because you have stuff happening in between loops here. And you do random access on the right-hand side vector, right? The right-hand side vector here, because it's a sparse thing, is getting accessed indirectly, right? So you loop over the matrix rows, and then you have this inner dot product here. So the way to do that, right, in Kokkos, and this is a bit, looks rather complicated right now, or quite a bit more complicated. But essentially, this is, this is kind of a really optimal implementation of like sparse matrix vector multiply for any like not completely degenerated matrices. And I'm going through that, because it shows, the kind of capabilities you have, right? So we're starting with a team parallelism here. What we are doing is we're essentially assigning a set of rows per team. And a team could be things like, threads on a CPU that share the same L1 cache. It could, it could be on a GPU, like the equivalent of like a CUDA block, which shares the same L1 cache, etc. And in this case, we're using three-dimensional things. We're telling it, how many teams we need, right? Because we computed from how many rows we do per team. We tell it we don't want to decide the team sizes ourselves. We just set an auto here, and we want a vector length of 8 in this case. This vector length would actually depend on, what the average length of each row is in reality. When we compute essentially the first row and the last row, within the team, and do a loop over those with this team thread range, which with the threads of the team, we figure out where each row starts, where each row ends, and then what we do is we do a reduction using the vector level parallelism. So each dot product is done essentially as a vector operation. And that will be vectorized, say, on like SIMD-based architectures, or mapped to things like sub-warp or warp level parallelism on GPUs. This 8 here actually means that we have that we use 8 threads, for example, on CUDA or HIP to do the vector level parallelism, which means we have kind of 4 Kokkos threads per CUDA warp here for those people who are familiar with CUDA. For those who are not familiar with it, it's fine. Basically, what we are doing here is we are explicitly exposing things like sub-warp synchronous programming in our programming model in a way which should be reasonably familiar even to people who have just written like CPU code, right? Because you can just think of it as vector loops, just that we map that appropriately on GPUs and deal with all the ways of how to optimally do reductions internally, etc. One neat thing here is I added this memory trait random access on the right-hand side vector because it's getting indirectly accessed. And what that does is it actually enables things like texture fetches, etc. on GPUs, which are some kind of access mechanism, a special kind of cache and access mechanism on GPUs, which optimizes for random access with locality, which is usually the case for our sparse matrix operations. If we then look at the whole thing, performance-wise, basically what we did here is we just run the CG-solve, which is essentially just a sequence of these 3 operations. And we did that, and we also ran it with replacing the SBMV, that last kernel, with calling the vendor library, things like MKL or QSparse or RockSparse. And this is running like 100 by 100 by 100 heat conduction problem, doesn't really matter. It's a pretty standard kind of finite element problem we are running as part of our benchmark suite for like procurements for the exascale machines and stuff like that. It's largely bandwidth limited. What we are measuring here is effective bandwidth, so it's essentially the algorithmic memory ops per time, which means that we are can potentially get more than like the global memory bandwidth of an architecture, because caching would increase the effective bandwidth we are getting, right? And if you run that for this kind of feed conduction problem, with this kernel above here, it turns out that we are getting roughly the kind of performance we would expect. I think the A64FX, which is the Fujitsu ARM chip, which is used in Fugaku, is underperforming a little bit compared to what we would expect from its peak bandwidth. But otherwise, we are basically getting something which is kind of equivalent to the bandwidth we would expect. It turns out that our kernel is actually slightly more efficient than the vendor libraries. It's a bit complicated why that happens. Largely, it's because this kernel is a bit better for like reasonably regular finite element codes and the matrices we generate, while the vendor libraries are probably a little bit better at somewhat less regular sparse matrices. It's a real effect, but I wouldn't like do too much out of it. But what it shows is, for something not completely trivial, right? Kokkos can actually achieve, the best you can write in the native models. As I said earlier, right, we are tracking new capabilities pretty aggressively. One of these is graphs. So CUDA introduced that recently. It's a thing which allows you to essentially write a struct or a description of like a dependency between different kernels, and then you can submit them and resubmit the same thing multiple times, potentially saving on launch latencies. So what this does here is, you create that graph, and what you do is you get this root node of the graph, and then what you do is you attach parallel operations to this. This then parallel 4 has the same syntax as our standard parallel 4. It's just that it's essentially attached to that root node, right? It takes the same things, right? It takes any of the policies or whatever, right? It doesn't really matter. It can be any length, so there's no restrictions on that, right? It's really like a normal parallel 4 call, which just gets attached to this root node, which then returns a new node. I'm attaching two other things here, two other kernels to that node, because they are attached to the same node, right? And they don't depend on anything else. These two things will be able to run in parallel at the same time. And then I create a new node, then all of these two nodes I got back here, that essentially is gonna create a joining and attach a new parallel operations to that. And that means this parallel for parallel reduce, I actually don't see what I have there because I have the videos here on my screen. Oh yeah, parallel reduce. So this parallel reduce then will run only after these other two have finished, right? And then you can resubmit that thing multiple times, right? That's a experimental capability which is now available and then maps to like CUDA graphs, but we implement that for the other, as it works on all the architectures. It's just that on some architectures it will not do anything special, right? It will just serially walk through that thing and dispatch one kernel after another. And that's a general philosophy, right, of us, that we do expose vendor-specific capabilities, but we generally give you a fallback implementation which doesn't hurt you compared to what you otherwise would have written, if that capability wasn't exposed at all. This is like a simple benchmark example, just running, like a couple of this kind of kernel thing there. And what you see there is that essentially just vector operations. And what you see there is if you have enough repetitions of this, right, so you have to amortize kind of the graph creation, which in CUDA graphs costs you quite a bit of time. But if you do that, then you can, you know, in particular for smaller problems, get quite a bit throughput improvement for this thing. So where are we with next architectures? HIP is basically done. There's some fine-grained tasking, as not the graphs, but some even finer-grained tasking where you can dynamically create graphs or task graphs on the GPU, right? So like with also tasks which can spawn new tasks. That's not implemented largely because the HIP doesn't support certain capabilities yet. We are working with vendors on that. We would need to implement that. On the other hand, the fine-grained tasking hasn't been used by many people at all. I'm not sure that we have any production users for that capability at this point. But yeah, otherwise, this is pretty solid at this point. We are doing PR testing, you know, for everything coming into Kokkos. It's tested on AMD GPUs at this point. There's a number of like, you know, smaller and larger applications which are working at this point. Performance is, depends. We found that one big problem we have on AMD GPUs is that they have significantly smaller caches than NVIDIA GPUs, which hurts a number of codes quite badly. We're looking at, you know, what we can do about it, but on the other hand, you know, we can't change the hardware you're running underneath, right, for you. But yeah, basically this is largely done, and you know, that is basically working. Aurora, which is the Intel platform, the Circle support is basically done as well. For the longest time, this was blocked by compiler issues. Like, you know, only at the beginning of this year, we really had compilers which were reasonably working. Like a year ago, the compilers were still like crashing on really simple stuff, like all over the place. And we basically found every other week, we found a new compiler bug, which was a complete showstopper. But at this point, this is working pretty reliable. You know, we are probably about like 3 months behind HIP in terms of how reliable this stuff works. But this is largely there, right? And we definitely expect by the time we actually have Intel machines coming in that this will be working properly. We are doing PR testing for this. We are essentially using the Intel compiler, but because it's LLVM Clang-based, you can actually target NVIDIA GPUs with it. So we are doing PR testing for that as well. So everything going into Kokkos is getting tested against, you know, not breaking anything with Sickle. There's a couple of capabilities missing, largely that has to do with things like arbitrary sized atomics. So we support atomics which are not just for natively supported types, but essentially for any types, using something which also is proposed for the C++ standard, actually made it into the C++20 standard, which is using effectively log tables underneath in some clever way. But for that, we need the capability of, at least in some way, have a global variable where we store like pointers for things like log tables. And Circle doesn't have that right now, but it should get that relatively soon. So that was a bit about the programming model, right? If you really want to learn about this, I would recommend, you know, the Kokkos lectures. That's something we recorded last year. It's 8 lectures covering most aspects of Kokkos, including also things like tools and Kokkos kernels, etc. You know, you see where we start with basic introduction, you know, basic parallelism, build system, etc. We talk a lot about, you know, views and what they can do. We talk about memory spaces, data layouts, why you need them, what you need to look out for, etc. We talk a lot about like more complex data structures, etc. A lot about hierarchical parallelism, how to use things like scratchpads on devices, etc. We talk about streams and, you know, execution space instance, tasking, SIMD. We talk about language interoperability, you know, how you interoperate with things like MPI, Fortran, Python, PGAS, etc. We'll have a module completely about tools, profiling, debugging, etc. And then Kokkos kernels, which is the linear algebra stuff. In total, this is about 15 or 16 hours of recordings, over 500 slides. There's something like 20, 25 exercises, which are also all available if you go to that link with solutions. There's an extensive wiki with API reference and programming guide, etc. And then, our Slack channel as like the primary support. Let me give you a couple of words for, the two other main projects. So Kokkos kernels is this BLAS and sparse and graph kernel stuff on top of things, on top of the Kokkos programming model and its view abstractions. It's scalar type agnostic, so these linear algebra things work for any types which also have the appropriate math operators. We use that, for example, for things like automatic differentiation types and uncertainty quantification types, etc. The kernels are layout and memory space aware. So if you can give it, views with generic layouts, and if we know the layouts, we call appropriate, kernels for it, and we can call vendor libraries underneath when available, right? So if you use a type combination and layouts which are compatible with the underlying vendor libraries, things like MKL or QSparse or QBLAS or whatever, we can call these things. Generally, the interface is a bit simpler than normal BLAS, largely because the views know how big they are and what kind of strides they have, etc. So if you call a gem in Kokkos kernels, right, you just handed alpha, beta, and the three matrices, as well as whether you want them to be transposed or not. But you don't need to give all these integers for strides and dimensions, etc. Another thing about this is it supports mixed precision naturally, right? Because it's all templated on every individual type. So you could have like one of these matrices being float and two double or whatever. That will just work. The interface, we also have interfaces to call Kokkos kernels at the teams level. This is this kind of nested level, think like CUDA block level. And essentially, you just handed this team handle, which you otherwise give to things like the nested parallel force. And that would then just execute, these BLAS calls using just that particular team. This could, for example, be useful if you have like, small linear systems or whatever in like scratch memory, right? If you have something in like CUDA shared memory, right? This interface allows you to actually call things for that, with each individual team, which is kind of neat. So Kokkos tools is, essentially our tools effort, which goes with the whole thing. There's profiling, we write our own tools and stuff like that, but we also work on interoperating or incorporating the support into like third-party tools. One thing, for example, is that NVIDIA added for us ways to name kernels, which means that your kernel names, the ones you can stick in front of like a parallel 4, would actually show up in things like NSYS, etc. Instead of just getting the C++ symbol name for whatever that kernel is, which end up being rather complicated, considering that our global function is just templated function on, which is templated on all kinds of internal stuff, as well as the functor or lambda you hand in, right? And the lambdas get like auto-generated names, which are a bit complicated. For auto-tuning, we have debugging, we have static analysis, it's all kind of interesting. Here you see that, right? If you use these kind of hooks, right? This is from vtune, and what you see here is you see this, parallel4.xb, show up. And that's essentially, a parallel 4 call, and the name you gave it was XB. And that would then show up in these tools using our connection tools. Generally, these tools are used via runtime hooks. You don't need to recompile your application. You just set an environment variable, and then, when Kokkos gets initialized, it will check, oh, you set that environment variable. I'm going to load this tool and then insert these hooks everywhere. The cost of having these hooks available but not used is practically zero. essentially you have things like per kernel call or other operations like allocation. You have a comparison of a function pointer to null pointer, right? So it really doesn't cost much. Here you see, it's integrated into things like tau, etc. So we've been working with a lot of these, third-party people, and a lot of them have implemented this stuff. Let's jump over it. Here, a couple of application results. This is LAMS, a widely used molecular dynamics simulation package. It's one of the top 10 codes in terms of hours, CPU hours used on the US machines, and also I think it's one of the top codes in Japan. And what you see here is the Kokkos version of this. It's actually a bit faster than the vanilla version on CPUs, largely because we've been optimizing. We force you to write better optimized code, then you get good performance on GPUs. Sparta, it's another big code we have. It's a direct simulation Monte Carlo code. This one has actually been running, on like full on, supercomputers, as the full systems, and we routinely do runs, with like a third of the biggest computer in the world with this. And you basically get what you kind of would expect based on bandwidth and stuff like that available on these things. Uinta was a different code from University of Utah. The reason why I show that is they actually had a GPU capability already. And when we rewrote their stuff in Kokkos, it turns out that the code ended up faster, largely because we used some tricks underneath, for making codes faster, which they didn't know about or so. Obviously, you can get the same performance as Kokkos, or maybe even better performance if you write in raw CUDA and you really know what you're doing, right? But honestly speaking, most people don't really know what we are doing, right? So it's not. We don't know all the tricks, right? Not everybody who writes CUDA code is familiar with every single capability of a programming model and how to get the most out of it, right? And so there are tricks we do, which for the average CUDA programmer, would make sure that our code will at least be as fast, and if not faster than it. We've seen that reasonably often. There are other codes, where that isn't necessarily true, where it takes quite a bit of work to get the Kokkos code to match the original GPU code. But most of the codes where we found that were codes which NVIDIA itself had optimized. So, yeah. One last thing before I'm stopping. As I said, we are also working really hard on the C++ standard. What we are doing there is essentially we are proposing new features for the C++ standard, which have been proven themselves in Kokkos. And what we then do is we actually backport these capabilities if they get accepted to current compilers, because we don't want to wait forever. And what we then do is we essentially wrap our Kokkos legacy interface around that backport, right? And that means our Kokkos legacy interface kind of can then use the vendor provided implementations of these C++ features when they become available. And the hope is that that in the long run will reduce the maintenance burden on our side. There's a couple of success stories where one of them is Atomic Ref, which is essentially provides atomics with all the kind of capabilities we had in Kokkos. And that actually made it into C++ 20. Before that, in C++, you had to actually use atomic types. So you couldn't in one kernel access that memory non-atomically and then in the next atomically, which was something we were doing all the time, right? And which is the way how the GCC intrinsics work, or CUDA works, or OpenMP works, etc. But C++ wasn't working, but then Atomic Ref essentially provides that capability, including non-native atomics, right? So it's actually a standard requirement that this works for things like complex double, right? Even if you don't have 128-bit atomics on your architecture. Another thing we're working on is Kokkos View, so our main data structure that is becoming stood MDSpan. The design of MDSpan is actually quite a bit better than the internal design of View, just because we learned a lot of things right while we wrote that thing. it supports arbitrary rank, right? So you could, in principle, do a billion rank, view. It's just that the compiler at some point crashes. It supports mixed compile time, runtime ranks, and we are still hoping that we hit C++ 23. But it's not quite clear whether that's going to happen because the progress in the C++ committee was a bit delayed due to all the COVID stuff, etc. Another thing we're working on is basic linear algebra, which essentially provides similar to the dense linear algebra interface of Kokkos kernels in the C++ standard. Okay, with that, I'm at the end, and we might have some time for questions.
Yeah, that was really great, Christian. Thanks for running over all of that stuff. Very interesting. So yeah, indeed, let's open the floor to questions now. And Attila is up first. So go ahead.
Yeah, maybe just to start the discussion. So thanks a lot for the presentation. I found it interesting in your talk that one of the things that I was preparing to attack you on was something that you didn't really focus on in the end, is that one of the big question marks I always have about Kokkos and even SYCL is how much we should be able to write like universal algorithms. Now, since you didn't focus on this too much,
I can give you an answer to that.
Okay, just because what I was going to say to this is that what we are finding, at least in HEP code more and more, or at least I find it more and more in HEP code, is that we may not be able to, at least the sort of algorithms that we are using, it's really hard to implement them efficiently for any sort of hardware. If we want to do some abstraction over AMD and Intel and NVIDIA, that's a very good abstraction, but you are writing GPU code or code meant for a GPU, which is a very nice thing to have. I fully agree. I'm just having some problems even with Intel claiming that, oh, you just write a single algorithm and it will work great everywhere.
Yeah. So let me give you a couple of answers to that, right? To different aspects of that question. So first of all, what we found is, right, that for the large majority of our applications, they've been running faster on CPUs after porting to Kokkos than they ran before. Largely because we give you a restrained programming model which prevents you from doing the stupid. Now, there are codes, which didn't do the stupid in before, right? Which didn't, like 10 years ago, decide, oh, on PGI compilers, it turns out that incrementing pointers individually instead of indexing into them is faster, right? Great. But so what we found is that generally about like maybe 60% of algorithms are trivially portable, right? So the algorithms themselves are simple enough that a simple expression of where your parallelism is will do, and then is mappable to any architecture,
I think it's good. It would be good if I specify what I'm having in mind, because what we come across very often is that we don't need to do the exact same floating point calculations all the time. This is what I meant with universal algorithms, that when we know that we will have a lot of floating point computation power, but we won't be able to execute different tasks efficiently between the thread, then we design the algorithm to do a lot of floating point calculations. If we know that we can have as many if statements as we want, then we focus on those.
No, I get what you're saying, right? So let me finish, right? So what I'm saying is that 60% of algorithms are trivially portable, right? There's practically nothing, you can do wrong there. There's another, 25% or 30% of algorithms or so, which are portable, performance portable, if you write parameterizable algorithms, right? For example, if you look at that SPMV I showed earlier, right? There's a lot of like independent parameters you can set, things like team sizes, you know, how many rows to give per team, what the vector length is, etc., right? And essentially what we do there is we choose very different parameters per architecture. For example, on normal CPUs, we usually run with a team size of 1 and give them a lot of rows, right? While on GPUs, we actually, other than this, you know, the threads reserved for like, you know, like vector operations, right? We only give you 1 row per thread, right? And by doing that, we can get that algorithm to perform super well across these different things. There's other places where we have specific abstractions. For example, we have a specific abstraction for scatter algorithms, which effectively under the hood changes between data replication approaches versus atomic updates based on the architecture you're running for, right? So on CPUs with low thread counts, we do data replication where each thread, you know, accumulates into its own duplicate of the data, and then there's a subsequent, you know, combining thing. While on GPUs we use simple atomics, right? But that leaves still a set of algorithms where you just have to choose very, you know, for optimal performance, you really want to use very different algorithmic approaches. And, you know, from our experience, that has been around 10% or so. It's, you know, in some cases, there are actually, you know, algorithms which would be performance portable, but the effort to write that thing or the complexity of that thing is actually larger than the complexity of just writing 2 simpler algorithms, you know, 1 for CPUs and 1 for GPUs. And we do that, right? It's actually not very hard to distinguish in this model between these 2 different things, right? You can just have partial specializations of algorithms and stuff like that. It still is a huge win if the entire program is written in the same programming model, right? So that you at least don't have to switch between like managing your stuff with CUDA, right? And thinking about CUDA in one part of your code, while in the other version of the code, you think about OpenMP or pthreads or TBB or whatever, right? You know, yes, you write 2 algorithms there, but you know, we often do even multiple different algorithms for different input decks, right? There's
and I'm fully on board with this, because even Intel started to change their messaging on this. That, well, if you've wrote one algorithm specifically for FPGAs, then you have that for FPGAs, but in the same language, you may have written something else to run on your CPU.
So what I can say is that that about half of the codes don't have any distinguishing thing there, from what I've seen. You know, half of the Kokkos codes don't have different algorithms or different architectures. They don't need them. The other half, you know, is looking at you know, a few, as a, you know, a small fraction of the algorithms need to be separated. So that's roughly what we are seeing right now.
Okay, thanks. I'll have another question later on, but after everybody has come.
Yeah, thanks a lot, Christian. It's very interesting actually to get that insight from someone like yourself that's been able to look at codes across many different science domains actually.
Yeah, I mean, we have about, in terms of users, right? Our current estimate is that there's somewhere around 200 to 250 projects using Kokkos, right? From all kinds of areas. So I think we have a reasonably decent view of the world at this point in HPC computing.
Thanks. Let's move on to Vince's question. You're next.
Hi, Christian. Nice talk. Thanks. My question is, okay, so I noticed, I guess, you know, Kokkos is, since you have a SYCL backend, it's more of a like a higher level, more feature rich is, I guess, is the impression I'm getting. But, you know, why, given that SYCL, you have, you know, different compilers for, well, LLVM, which can target Intel, NVIDIA, and AMD GPU. What is the benefit of Kokkos? Is it the ecosystem, like the more features that you have available, the you know, specialized libraries for doing specific, you know, mathematical functionalities, or what is?
there's a very blip answer, right? And that answer is that Kokkos at least works right now, while Circle still runs into lots of problems because the compilers are so young and so buggy. Like, for example, the LAMP Circle stuff people have been working on is still about a factor of 2 to 3 slower than what the Kokkos version of this is right now. And some of the algorithms in LAMPs don't work with Circle yet. That's a bit of a blip answer, right? Partly that is because Circle is so much younger, right? The real answer, I think, is that you do not have vendor buy-in from everyone into Circle right now, right? Like NVIDIA is not supporting Circle and is not planning to support Circle. AMD is not really supporting Circle either, right? And right now, Intel is paying Codeplay to develop the NVIDIA support for Circle, right? Which is nice of Intel to do, right? And it works reasonably well. But it means that, for example, new capabilities in GPUs on the NVIDIA side are not exposed and are not getting exposed, right? Because the incentive of Intel to pay Codeplay to expose all the features in NVIDIA's hardware, which their GPUs doesn't have, right, is rather smallish. Does that make sense?
Yeah, absolutely. Yeah, that's a good answer. Okay, that's kind of what I was thinking, yeah.
Yeah, and so Kokkos, right, as being funded by DOE, which has a vested interest in making all of these platforms work as good as possible, right, is effectively this neutral platform in between, right, which tries to expose all the goodies from everyone, right, in the most, pragmatic way we can. And we do have quite a lot of support directly from the vendors, right? So at Sandia, our entire code base, which targets GPUs, which targets all the new platforms we are buying, right? And not just we have a number of codes which are saying just, okay, we're just gonna not bother with this, right? We're gonna work on legacy platforms, on CPU platforms, for however long we still support this code. But all the newer codes, everything, right, is written in Kokkos at Sandia. And a good chunk of the codes at other labs are written in Kokkos at this point, right? Which means that the vendors have a lot of incentive to make this work. So they, for example, AMD and Intel NVIDIA and Cray have Kokkos as part of their compiler test suite, right? So when they make changes to their compilers, they actually run Kokkos through it to see if they break us.
Okay. Yeah, I guess I'm partially sold. Thanks that's a very nice answer. I guess the other thing is, when you think of performance portability and actually how you measure or quantify, where you lie in terms of what you'd expect from optimized libraries or something like CUDA. Okay, never mind. That's good. Thank you. Thanks a lot.
I can talk a little bit about that. I can actually even show you some interesting numbers from external people on that. So generally, it's hard to do that comparison for large applications, right? Because nobody writes their large applications in 5 programming models just for the purpose of comparing the programming models, right? So we've done that with like mini apps a lot, right? And in mini apps, what we find is we get pretty much on par on the GPUs, and sometimes a little bit below, like 10-15% or so on OpenMP on CPUs. Largely that has to do, we track that down to use of lambdas. So lambdas don't get as optimized. So if you use raw OpenMP and you use lambdas instead of just writing the OpenMP loop, the code gets slower. Some of that is getting improved now because that's the way other people have been writing their code, right? I mean, if you look at the C++ standard, everything is getting written in lambdas, right? Google writes everything in lambdas. Facebook writes everything in lambdas. And that means that, LLVM and stuff get a lot of optimization work done right now to make this work better, right? What we found is we can recoup that if you use explicitly SIMD. We have a new SIMD class, which also works on GPUs. And so if you use that explicit SIMD kind of stuff, you can largely get the full performance back and match whatever we've been doing before on CPUs. And that is obviously for fully optimized codes, right? Comparison, not for like the typical code we have, which turns out to be, somewhat suboptimal. here, this is an interesting numbers. This is coming from a report by some external folks for the what was it, climate change code. And what I did here is I took their performance report and divided it by peak bandwidth on each architecture, right? And what you see here is that, over a wide range of architectures, including like GPUs, and things like KNL and Power and ARM and different Intel architectures, you're within like, 0.6 to 1, right? And it is expected that this kind of stuff is kind of bandwidth limited, right? And considering the differences in caching and whatnot, right? I feel that this is a pretty good sign, for decent performance portability, right? I mean, this is completely ignoring, whether this algorithm is cache limited or not, or what not, whatever, right? It's just dividing by peak bandwidth, and that's it. And getting there within like 0.6, across this set of architectures, I think is a pretty good sign of success. I don't know if you agree with that statement, but.
Half is good. Yeah, and the Python bindings or the Python support is, I think, going to also be super useful. So it's nice to see that. Thanks a lot, Christian.
Yeah, thanks. So next we have actually a bunch of questions from Ricardo. So if you are able to ask them, Ricardo.
Yeah, can you hear me?
Yeah, it seems to be okay.
Yeah. Okay, that's good. So I have a relative few questions, but probably there are yes or no questions. So maybe it goes fast. So first question is, when your lambdas get bigger, at least this is what we experience, you begin it by register spilling. And then the layout of the memory of your data matters a lot, in the sense that if you have some dynamic data, then it matters a lot whether you try to minimize the interaction that you need to manage this data. Do you optimize for this? Do you have use cases where you have where you have a lot of logic in the lambdas?
Yeah, I mean, we have codes. I think the biggest kernel I've seen was about 10,000 lines after inlining.
Okay.
So
okay.
We've done that. We do some optimization under the hoods. For example, depending on your lambda size, we decide things like where to store the lambda, like whether we hand it as an argument or we store it in constant cache, etc. That, for example, helps a lot with like register spilling, right? If you don't hand it as an argument, a lot of the if you hand it as an argument, right, a lot of it ends up in registers. If you put it in constant cache, it's almost as good as registers, but takes away from that. We do other things like we look at register pressure, change like block sizes, etc., and whatnot based on that. The layout of your data itself, generally, we work pretty hard in the applications to never do like pointer chasing. So a lot of the data structures we have are more like CSR data structures, right? Where you have like index-based data structures or sparse data structures, instead of like jumping through different memory locations. We support all kinds of data structures, right? As I see your question, do you support rich data types such as not sum types or native structures of arrays? You can basically use arbitrary C++ data structures in our case, right? You can store arbitrary data structures inside of Kokkos views. You can use them, you can capture them, you can, you just have to mark up the internal operators and whatnot with the correct like markups, right? But we've been using all kinds of crazy stuff.
Okay. Then the next question, let's say on the hardware side, I saw that you were waiting for compilers to be ready in the cycle compilers in particular. Could you, in principle, write a backend based, I don't know, on some CAPI like the level 0 or OpenCL, at least in principle, to have a feeling on how you rely on the C++ native hardware, let's say the native hardware support?
Now we need a C++ compiler, right? There's no way around a C++ compiler. I mean, our model is written in C++, right? And in order to be performance portable or portable at all, right, it needs to be C++. I mean, it's all templates. Yeah,
the user side of this, yes. But I guess you could use a CPI behind, no, to implement your.
Yeah, but there's really no good reason to do that from what I can see. the OpenCL, you know, I'm not sure. As it's not really supported by all the vendors anymore, and like NVIDIA has not been supporting it really at all for a while. It's not clear to me that Intel will have SYCL be OpenCL based for long, right? I mean, if you look at level 0, right, it's clearly a replacement of the parts of OpenCL they've been using SYCL.
Absolutely, yeah.
Right? So I don't know. I don't see any use case for that right now. We are looking at using SYCL for the FPGA side. We'll see how it goes, and we are working on some other stuff for non-disclosable. Actually, no, I can tell you, we are working with Next Silicon, for example, right now on support.
But I guess at that point you would have a very different project anyway. If you wanted to talk to like low-level libraries, that means that you would be developing a compiler yourself.
Yeah, we are not going to developing a compiler. There's actually other people who did that. Los Alamos developed a version of Clang where they directly intercept things like Kokkos Perl 4 and translate it into Perl IR without going through our template headers, which is pretty cool. But it's a subset, right? They never went to supporting the entire programming model. Okay, last question here. You mentioned a lot of atomics. We experienced massive performance drop if the emulated atomics were not available. Are your reductions really performance portable? Yes, our reductions actually not use atomics. They are doing reduction trees and all kinds of other nasty things, but generally don't use atomics. And our atomics are reasonably fast. So even our emulated atomics, I mean, we're not as fast as the hardware atomics on GPUs, right? On CPUs, it's pretty okay because they don't have good atomics anyway. On GPUs, our fully emulated atomics are roughly on par with like maybe 10–20% slower than cast loop atomics, from what we can tell. And the cast loop atomics are about like a factor of 8 or so slower than the native atomics.
Yeah, that's interesting. Yeah.
Right.
Yeah, we suffered a lot from this because certain algorithms match, let's say, can express very, very conveniently with atomics. But if you don't have that, then you have to go through tree and so on and so forth. That it's quite complicated if you have to do it a lot. So then, in this sense, I'm happy to see that you have this type of solution that is indeed portable. So that answered my question.
Yeah. Our reductions are pretty decent. I mean, they are way more decent than the SYCL reductions are even right now, I think. So the native reductions in SYCL and OpenMP target for the longest time were really bad. Like, I mean, we gave the compiler vendors examples where our own reduction, right, in CUDA was like 100x faster than like the OpenMP reduction. And we were like, what the hell are you guys doing?
Yeah, okay, thanks a lot.
Thanks a lot for the questions, Ricardo. Then we have Stephen now. Let's ask the next question.
Hi. Thanks for the wonderful talk, first of all. It was very interesting. So I have a little bit of a more philosophical question, maybe. But if we look sort of at the performance portability space, we see a big move in terms of C++ towards a more higher level programming, a higher order programming model. So I'm curious, do you think that pursuing performance portability in C++ is sustainable, or will we eventually need to move on to something like FootHard or a different kind of more functional level? Should we eventually move to, is C++ going to be viable for performance portability in the future, or is it not the right kind of language, do you think?
So I think compared to some other languages, C++ has a lot of advantages and a lot of ways how it probably is the right thing to do for, like, in some sense, the low level stuff, right? Largely because C++ is a language which allows you to write complete models, right, in itself, right, embedded. I mean, that's the reason why you see a lot of this kind of abstractions written in C++, right? Because C++ is the language which allows you to do that in a really performant way, right? Without writing new compilers completely. And if you look at what's going on in the C++ committee, right, in terms of movement to support some of these concepts and some of these ways, right, I'm I'm pretty convinced that C++ will be around as the performance portable solution going forward. There will be other languages like Julia, for example, looks pretty promising, you know, and a number of other things. But the ecosystem around C++, right, in particular also outside of the HPC community, is so vast and huge, right, that that I think it's going to be one of the primary ways of doing this for quite a while to go, right? It's just that there's so many tools around it, right? So many vendors writing tools for it, you know, when the whole ecosystem around LLVM and whatnot, right? I think it's going to be hard to replicate that and in something else, right? And even if you could write a language, you know, and you could design a language which is a bit better optimized for your domain and stuff like that, right? The benefit you need to get from that must be really large in order to compensate for all the drawbacks of not having the ecosystem around C++ available, right? I mean, think just about the amount of money the vendors throw at the C++ compilers, right? I mean, that must be, you know, probably 9 figures or something like that, right? In aggregate. And I mean, who is going to finance that for any other ecosystem, right? The only other viable things I could see, you know, large scale, could be, you know, somebody like Google doing their own thing, right? They have the resources, or Facebook or whatever, right? They have the resources to write their own compilers and optimize them as well and write all the tools around it and have the whole ecosystem developed on their own around it, right? But on the other hand, that stuff is then probably optimized for the use cases of Google, right? And not necessarily the larger you know, ecosystem. On the other hand, Google is so large, you know, that their use cases probably encompass a lot of what other people do. But still, at this point, I think C++ is the most viable of these things. And that's a big problem, you know, with Fortran on our side, because we don't have the ecosystem around it, right, anymore. It's hard enough to get a compiler out of these people. I mean, that's why DOE started with this Flang project, right, an F18 project to get an open source LLVM-based Fortran compiler. But I mean, if you look at how the progress on this thing is, right, we've been working on that and throwing millions and millions and millions of dollars at that thing for years, right? And it's still not working.
Just a very quick question on this. I know that Intel is trying to port their Fortran compiler to LLVM. Is there any collaboration on what they are doing?
Yes.
Okay.
But it's all still not working, right? We are still using the legacy Fortran compilers, and it's a very, you know, it's a very difficult situation for some of our codes. There's a number of these Fortran codes which decided because of that to go to C++ and stuff like Kokkos, and you know, that's also why we do this interoperability, right? So that they can incrementally port, because it has been really hard, and the way the initial like Flang development crashed and burned, you know, was very discouraging and very worrisome for a lot of people.
Thanks a lot for that insight, Christian. I don't see any other hands up. I wonder if there's any final questions before we close. Nope, I'm not seeing any. Okay, so I think at that point, we can then bring the meeting to a close. So I'd like to thank Christian again for the extremely informative talk, and for how it was really an excellent discussion afterwards, touching on many interesting topics. So yeah, thank you to Christian. Thank you to everyone that contributed.
You're welcome. Thanks for listening.
And yeah, we will meet again for the next Compute Accelerator Forum in October. So I look forward to seeing you again then. Okay, thanks everyone.
Bye-bye.
Bye.
Bye-bye.
Bye.